have this definition of equivalence, homeomorphism, but we would like other kind of definition of equivalence. For instance, can we find, so because intuitively for us in the three-dimensional space, these two objects are not the same. So with the intuitive idea of deformation, we cannot deform this one to this one in the three-dimensional space. It's impossible. Without cutting, it's impossible. So there is other definition of equivalence, and this is isotope. Under isotopy, these two spaces are not isotopic. So let me say, so isotopy is intuitively is that notion that you learn about homeomorphism, is continuous deformation. But when we say continuous deformation, it's because there is an ambient space where we can do the deformation. Intuitively, this is continuous deformation. But when we say this, it's because there is an ambient space. So that is the difference. So formally, mathematically, is that so we need now three spaces. So x, y, and there is the ambient space. So let's say that the ambient space is R3, that would be more general. So we have subspaces of R3, and we say that they are isotopic. There is an homeomorphism H from R2 to R3. And in fact, it's stronger. We need that is orientation preserving, so we don't switch the orientation. Such that h of x is equal to 1. That is the mathematical definition, but intuitively it is this definition. So these two spaces are not isotopic, but they are homomorphic. We have these two relations, isotopy, isotopic. So which one implies which one?
Isotropy implies homeomorphism. Yes.
So isotopic implies homeomorphism. And this is an example to show that the opposite is not true.
Yes.
They are homeomorphic but not isotopic. We can give other examples, but this is not true. Two homeomorphic spaces which are not isotopic. But we still need to justify why they are not isotopic. So this is like intuitively true, but we need justification. So can someone give other example? Of two homeomorphic spaces which are not isotopic. Similar to this kind of space. What happens if we twist 3 times? So we have our piece of paper and we twist 3 times. This one is homeomorphic to what? So if we twist once, only one time, is the same space or not?
Sometimes visualization is difficult.
Yes. So if we twist both number of times, they are always the same space. So they are homeomorphic. And the justification is the same. If we cut, and we untwist, and we glue again, there is no problem to glue the same points coincide. But if we twist, and also here, like if we twist 4 times, well, I can twist 4 times. So these are the same, they are homeomorphic, but they are not isotopic. So, and this is the same, the justification is the same. We can cut at any point, we can cut, and we keep the information, and we can do what we want, and we try to do again, and we see that the points coincide. And if we can do that, we can do again, and the 2 spaces are homeomorphic. But if we try to do this with this, or this with this, we cannot, because
How can we define the twisting in mathematics?
twisting is a rotation.
I think that h of x is like h of x equal to 1. I just want to see when you're twisting it, for which x in this diagram it is not equal to y for isotopic. You're not saying these are 2 are isotopic.
These are not isotopic. But we need more, I will explain how to show that. For instance, how to show that. Like, suppose that they are isotopic. So if they are isotopic, there is a map like that. But that map, we preserve that, so let's call this x and y. If they are isotopic, there exists some map from R3 to R3. Such that h of x is equal to y. But moreover, we call this C1 and C2, and this C1 prime and C2 prime. So in particular, this gives a homeomorphism from x to y, because we have this implication x. So it means that H of C1 union C2 should be equal to C1 prime union C2 prime. But these two one-dimensional objects, they have a property here, is that they can be separated. But these two here, they cannot be separated. And this is, I will talk about this, what is this means to cannot be separated. So there is some linking between them. I will explain that. So they cannot be isotopic because, so if they are isotopic, the behavior of the two one-dimensional objects, C1 and C2, should be the same as this behavior. And they have some difference. But this difference is something that is related with the ambient space. Because both of them are just two circles. But here they are separated, and here they are linked. Yeah. But this nothing is something that is related with the three-dimensional space. But we will come to this in some minutes. Are there any questions about this? So, what is the conclusion? If we twist an even number of times, it's a cylinder. If we twist an odd number of times, it's a merisma, a homeomorphic space. And all of them are non-isotopic. So we have now two notions of equivalence, and in fact there are many notions of equivalence in topology. So there are other one which is homotopy, which is the origin of topology, algebraic topology. So we also have homotopy, or being homotopy space. There are other notions. And there are more. There are many notions depending on the space. If the space are metric space, we have isometric spaces. And there are many notions. Okay, so depending on what you want to study, you take the notion of equivalence that you want. What we want to study is this. So it's important that for this notion we have ambient space. Any question or comment?
So which one is stronger condition for equivalence? They are like described as topic, homeomorphic and homotopic, isometric. So they have different behavior. So when we say that which one is like homotopic, like these are the some, according like in fundamental group, there are some classes, something like that. So which one is more stronger? Like
so this one implies homomorphism and implies homotopy. So until now this is the stronger notion. So two spaces are isotopic, they are all of them. But there are other ones more stronger. Here. There are other equivalence notions of equivalence which are stronger than the second. So maybe who can give an example of two? So I didn't give the definition of homotopic spaces, but some of you know about this. So who can give an example of two homotopic spaces which are not homeomorphic?
We are waiting for instruments, otherwise
So who can give examples of homotopy spaces which are not homeomorphic.
Some, I think they don't know homotopy.
Definition of homotopy.
So homotopic is like it's also like deformation, but it's stronger than deformation because we can collapse something. For instance, cylinder. This cylinder is homotopic to circle because we can slowly start to collapse the cylinder. So this operation is continuous. So these two are homotopic, but they are not homomorphic. So this is two-dimensional object, this is one-dimensional object. But it's not important. Important notion for us are these homeomorphic isomorphic. This one is easy. Isometric, you are very familiar with isometric. These are homomorphic and non-isometric. Question or comments? Are all of you familiar with the Euler characteristic? Euler characteristic. So Euler characteristic is the origin of topology. Very old.
In polyhedra, vertices minus edges plus faces is always equal to 2.
Yes, for the spheres. That is very famous formula.
Yes.
And that is the origin of topology. That is the origin. So you have that famous formula that say that in the plane, so we have the plane and we make any graph and there are no restrictions on the graph. No need to be connected, no need to be a simple graph, or we allow loops, we allow several edges between the vertices. We allow uneven vertices. And no matter what kind of graph you draw in the plane, there is always this formula. Vertices minus edge plus face equal to. We only need to define what is a face, but faces are, so there are two kinds of faces. So the bounded regions, like this one, and also the exterior region. So in this case, we have 1, 2, 3, 4 faces. In the vertices, 1, 2, 3, 4, 5, 6. And edges, we have 1,
8, I think.
and it gives 2 all the time. So this seems always like magic. Like the elementary school students make that and always gives 2. This is very beautiful here. And this is the origin of topology. So this this is the Euler characteristic, but we can define Euler characteristic for any kind of topological object. These kind of objects we can define Euler characteristic. This is Euler characteristic of the sphere. Because we can see this drawing in the sphere. The plane and the sphere is almost the same. But the difference is one. Euler characteristic is the oldest, like, no. Then I can add two other vertices. So we add one face. So now we have 8 vertices, 2 edges more, and 1 face more. Still the same, or not? Faces. 1, 2, 4, 5.
Is there any condition of connectedness here?
Connectedness is required. Connectedness is required.
Maybe connect.
I think connectedness is required.
If we take a null graph only set of vertices, then clearly the formula will not work.
Yeah. So we need connected graph. Maybe we don't need connectedness. We need is that the regions are always disk. The regions are always disk.
Take the circle, do the joint circles, it doesn't work.
Yeah, but it's because the stereo region are not a disk. If the regions are disk. Any other question or comment? So we want to do this, but for the torus, for instance. So let's do the. So now we change the space. Now we live in this space. And we want to compute the Euler characteristic. So the Euler characteristic will be some kind of number such that any graph I draw there, with the condition that the faces are disk, and I compute the number, is always the same. So for instance, if this graph, so we have one vertex, one edge, but the regions are disk or not. So what is the region? So I cut along the graph. If I cut, we get cylinder. So it's not a disk. So this I cannot compute the other characteristic. So what we need to add to that? We add this edge. What happened if we cut? Like cutting now here. So this gives disk. So now we can compute the other characteristic. So how many vertices? 1. How many edges? 2. And how many faces? How many faces?
3.
Three. Formulas. We know the formula, so we can guess.
I just want to cut it from the top.
I can cut along the red. So I cut, if I cut here, I just change the I cut the green one, I get this cylinder. And this, the red one, becomes this. And this point, the same A, is the same as this point A. Now we cut along this one. So if we cut along this one, we can open, we obtain squares. And this is red, this is green here. This is green. And this is red. And this point, like every time I am here, this point is the same as this point. This point is this point. And also from this side to this side. So that is the meaning of cutting. But I can draw more complicated graphs and cut. And that will be difficult to draw. For instance, if we do something like this, we can cut also. And it's still the same drawing, but more difficult with this one. So how many faces? Which are the two faces? So some people say 2, other people say 3, other answer.
With the help of formula 3.
But the previous formula was for the sphere.
Right.
It will be not the same here.
One at the top, when you cut,
Yes.
there will be 2 faces.
But if we cut this one, right, let me grab no more colors. So faces are something that we can color. So let's start with colors. If I color this part, this is orange, 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 orange. All agree that this is orange, but I can continue behind. So I continue coloring behind, and I arrive here orange, still orange, orange, orange. So how many faces? One. One. And is this one here? So the faces appear when we cut. So there are only one. So the other characteristic for the toes is this one, still. Any graph that we draw in the toes such that if we cut, we obtain this, will give this number, 0. Any question or comment?
So we don't need to draw this in a plane.
No, it's very abstract. So because the space itself is abstract.
So that's why I gave
This is
wrong
the-
answer too.
This is the torus. So we can compute the other characteristics.
Everything is this thing. So we don't need to plot it inside another in a sphere system.
No, because we can, so this we can draw like this. It's still the same object. This is still the torus, but it's
Perfect.
embedded in the three-dimensional space in a different way. But as a topological space, they are homeomorphic, same space. They are not isotopic, but they are homeomorphic. So if we do the same drawing here, and the graph, and we cut, we obtain same formula. In general, we draw the torus like this, but it's not good for understanding because people say, oh, the torus, it has one hole. We can see the hole there, but here we cannot see the hole. But we can compute with the numbers. We can compute. So the number of holes is this formula. So this is Euler characteristic. The letter is this. I don't know the name.
Sky.
Chi of torus. And there is a formula relating the Euler characteristic and the number of holes, the genus. The formula is like this. So for the sphere, this is 2. So the genus is 0. For the torus, the Euler characteristic is 0, so the genus is 1.
1.
Any question or comment?
Sir, this formula works in general always? Or maybe this has some restriction like previous one?
Which formula?
This
Euler characteristic.
these are used.
And the relation of the Euler characteristic and the genus? Or which formula?
Euler characteristic.
Can you use the cylinders?
टोरस के लिए तो सेम ही है ना, वो तो आप टोरस सिंगल होल वाला होगा, डबल का ट्रिपल का वो सेम आंसर होगा। फॉर इंस्टेंस अगर जी 2 होल वाला होगा तो -2 आ जाएगा फिर आइलर का।
This formula is only for surface.
Yeah.
Yes, I asking for the surface and different things.
But for example, for this does not work because there is boundary. So for boundary we need to modify.
Compact surface without boundary.
This is for surfaces with compact.
Yes.
If we add boundary, so the formula is like this. This is the number of boundary components.
So if we puncture torus, then it becomes -1. Yes.
We make
So
let me
if we
make that
puncture
example.
this torus, then it becomes -1.